It's my pleasure to welcome our plenary speaker for the day, Sunita Saravagi, who I think needs no introduction for most of you. Sunita did her PhD from Berkeley, had a stint at Mountain View with Google, and she's also faculty at IIT Bombay. So without much further ado, Sunita, over to you. Thank you.
Good morning, everybody. So today, I'm going to be talking about neural models for sequence-to-sequence learning. Deep learning, as you have all heard, has achieved remarkable success in many different tasks. And a large fraction of these tasks can actually be cast as sequence-to-sequence learning problems. Before deep learning, these tasks, I'll include examples from translation and speech recognition and grammar error correction and image captioning. All of these were earlier solved in their own silos using heavy domain engineering and a bit of statistical learning. And with deep learning now, we have gotten remarkable accuracy in all these different tasks. Surprisingly, a very simple model has been capable to surpass these domain-specific numbers, and that is this soft attention-based encoder-decoder model. So this talk is going to be actually a critique of this very popular and much loved model. So it's a bit of a negative spin of a talk. So basically, so first let me just crisply define what I mean by sequence-to-sequence learning. Your input is a sequence, and we are going to denote the different parts of the sequence x1 through xn. So like when you are talking about tasks like translation, the xi's denote a word in a sentence, and the output is another sequence. While the input could be non-word, like non-discrete also, like a vector denoting an audio frame, the output we are going to think of as discrete tokens, and they typically come from a large vocabulary, and so therefore there is a huge amount of possible outcomes that you will have to deal with, the complexity of outcomes. And this particular many different applications can be cast as sequence-to-sequence learning problems, as we will see through examples here. So the first major task which was tackled by deep learning in terms of surpassing conventional results was translation. So when you think of translation as a sequence-to-sequence learning problem, you have an input X, which is the sequence of words in a source language, and your predicted Y is the sequence of tokens in your target language. You can think of each of the words here as a YI. So this is the notation we are going to follow throughout the talk. And before deep learning, translation systems were kind of driven by a huge amount of linguistic specific domain knowledge specified as either transfer grammar rules, and they were painstakingly developed by linguistics. There were sort of elaborate phrase translation tables, and then there was this thin layer of a statistical machine learning model to stitch all these things together. Whereas modern neural deep learning systems, they score almost 60% better than these traditional systems, and they are based, and they use very little domain-specific engineering. All that you require is a huge amount of data. So the next task, say in speech recognition, again your input X, you can think of as sort of, by some magic, you have taken your continuous audio frame and you have broken it up into frames, and that is your input sequence, and your output could be words or phonemes in your target language. And this is another area in which modern deep learning systems have achieved remarkable accuracy. A problem which currently we are focusing on is grammar error correction, where you can use a deep learning system to sort of replace an English teacher in terms of at least solving the task of automatic essay correction. And recent systems have achieved higher accuracy than the inter-annotator agreement accuracy on a well-established benchmark for grammar error correction. So across this very diverse tasks spanning many different communities, the one model which has worked for them is this soft attention based encoder-decoder model. And over the last 5 years, we have gotten this amazing accuracy using at the core just this very simple model, and of course huge amounts of data and large GPUs and other things. Those are mentioned only in the footnote. Okay? And so the first thing that the encoder-decoder model did is to take this big bold step of modeling the full dependency among all the tokens in your output sequence. Some of us who grew up in the tradition of hidden Markov models and conditional random fields, we are very scared of creating complicated, large, long-range dependencies among output variables. So typically, the techniques used in early systems would assume that if you are outputting a token in the tth position, then that token would only be dependent on its directly dependent only its immediate neighbors, and it would be independent of other tokens outside its immediate neighbors given its immediate neighbors. So that was like a common conditional independency assumption which was made. Now the brave new researchers of deep learning first assumed that when you are trying to create a probability distribution of y, the output sequence, which consists of these capital T variables y1 through yt given x, you are going to just apply plain chain rule factorization and not assume that this yt is dependent only on a subset of this previous yt minus 1. You attempt to model the full dependency among all previous t minus 1 variables for every yt that you observe. This is very scary. You know, from a graphical model's viewpoint, when you think of drawing this Bayesian network, every variable has as parents all preceding variables, and learning parameters gives rise to huge sparsity challenges if you think of them as discrete conditional probability tables. And inference becomes impossible, right? I mean, this is like obviously a hard problem. But people went ahead with this assumption in any case and came up with this clever architecture, which I'm going to go through step by step on how they embraced such full dependencies. Okay? So the first thing that is done is to take the discrete input sequence and create a soft vector representation of this input using either RNN like a LSTM, or nowadays the fashion is to have this self-attention based transformer blocks which can process the input in parallel, and you take this discrete input of input sequence and you create for each input token a vector representation which intuitively captures the contextual meaning of each word. Okay? Think of H3 as sort of a soft representation of X3 in the context of the full sentence. Okay? Yeah, and now the main thing that people like us are scared of is how do you handle the dependency over all previous yt minus 1, y1 through yt minus 1, and there again you use the LSTM or RNN or transformer magic and you convert it into a sequence of vectors where you can think of the last vector that you produce as somehow a summary of all the previous y1 through yt minus 1, and now you are ready to create a binding between the summary of the previous tokens that have been generated and each of the inputs. Now, when I'm going through this, think in terms of a translation example. So when you are trying to generate the next word in a target translated sentence, you of course have to look at the input, okay? And typically there is a word-to-word kind of means synonym translation kind of thing which happens when you do when you try to produce your output token, and that you can think of as an alignment between the input and the output tokens. So before you can generate the next token, a natural next thing to want to do is try an alignment between the input and output. And in these modern encoder-decoder models, such alignment is handled through what is called an attention layer, which will give you for each of the input positions the relevance of that position for generating the tth word in the output. So it's like, if there is and that relevance is expressed in a soft way in terms of probabilities. So probability of A3 will tell you what is the likelihood that the third word is going to be translated when you generate the tth word in the output. So that is the soft attention. And now, in order to make sure that your model is differentiable and all that, there is one sort of hacky thing which is done, that you take a weighted combination of the input state with the attention distribution, and you get this result that you get, which is called ZT in my slides. So ZT you can think of as a diffused soft representation of the input word which is currently being translated. Okay? And that is used along with the decoder state which captures the language model of the target sentence to generate the tth word. So this is how the daunting full dependency is handled in the encoder-decoder model. In summary, we depend on the soft attention to do the alignment, and we depend on the decoder to represent the variable length history as a fixed vector. Okay? And now, once you have created this architecture, the training is done. Because you have a full probability distribution over the output, you can just resort to textbook maximum likelihood principle for training the model. So if you are given a data set where you have examples of correct input output pair, you just have to maximize the log of the probability of each token given its history. And because of this chain rule factorization, and because you know all the previous token in the training data, this training actually is in fact no harder than just training a logistic regression classifier. So it's like if you have n training examples, each of length t, it would be like you have n times t independent examples over which you have to build a logistic regression classifier because of this kind of factorization that you are doing. So training is easy because it decomposes over tokens, it's efficient, it's parallelizable, and it's quite practically doable even over millions of examples. Okay. Now, the gotcha comes in the inference part. So during inference, you are given an input x and you have to generate the y sequence. Now, because of the dependency, the full dependency that you have assumed that each yt could depend on on the entirety of the previous y's, you cannot find the sequence which has the highest probability in polynomial time. So inference has to be done approximately. So people either use some greedy decoding or a small improvement over the greedy decoding, which is called beam search. So beam search is sort of like a top K version of the greedy algorithm. So this is how inference is handled. So this is basically a very quick one slide overview of the encoder-decoder model for sequence to sequence learning, which we are going to critique through this talk. So but first let's look at the positives. Right? So one of the big sort of achievement of these models is that because they capture the full dependency in the predicted tokens, they do not have any bias. The model itself does not include any bias, and this was so much unlike CRFs and HMMs, which after a certain amount of training would saturate. No matter how much data you gave it, it could not continuously improve. Whereas these models, because they do not make any assumptions of conditional independencies, typically the more data you give them, the better. They keep on improving in terms of their accuracy because the model has high capacity. Okay? And the training is simple. because if you remember, some of you, if you remember training for CRF models or training for structured output models, you had to solve complicated inference tasks at the time of training. That is not required in this Bayesian kind of factorization. And of course, you have obtained record breaking accuracy gains across diverse applications. So these are the positives about the encoder-decoder model as currently being used. But we are researchers, we don't want to just rest on our laurels, so let's look at the brickbats. Okay. So what are the negatives? In this talk, I'll be able to focus on 3 problems with this encoder-decoder model. And at least for 2 of them, I will show surprisingly simple solutions which fix the problem when you think about the model from a more principled statistical grounding. Okay. So first we'll talk about attention. Okay. So attention is what is, so you should think of attention as a random variable, and the tth random variable AT tells you what is the what part of the input is relevant for producing the tth output. And so because the attention is about the alignment between the input and the output, right? So you expect the alignment distribution to somehow be a function of both the input and the output. But if you look at the way the alignment probability is handled, the attention probability is handled in current encoder-decoder models, you will find that the output yt is very distant from AT. You never explicitly model the joint distribution between them. So you compute the probability distribution over the attention, of course, without knowing yt. You only compute this based on the decoder state, which has only seen y1 through yt minus 1. Okay. So you compute these attention probabilities. Then you create a hacky diffused marginalization of this attention probability with the encoder states, and you get this context vector zt, and thereafter you have forgotten about the attention variable, and you attempt to produce the output only in terms of this zt. Okay. Now, so that's a big problem. If you think the right way to do it, the way a sound statistical model would capture attention and the output, that would be through a joint distribution. So if I'm trying to create a probability distribution over at time t over the output tokens y, given a bunch of encoder states in the input, and attention is my hidden variable, so I should actually be marginalizing outside over the attention variable. So over all possible values of the attention variable, I should be computing the probability of the attention and then trying to create the probability of y given that attention. So this is the correct way to handle a hidden variable which determines the output. In contrast, what is done in current models is to create a probability distribution over y over this hacky conditioning where you early marginalize the input states. There is no sound probabilistic basis for such early marginalization. Okay. So our first work was try to realize such explicit joint distribution between the attention and the output variables. So when you do that, now the model diagram looks different. So up to the point that you compute the attention distribution, it's the same. But thereafter, we will not first marginalize out the attention variable by taking an average over the hidden states over the input states. Instead, for each input state, we will create a probability distribution over the y. And this is where we will do the explicit joint distribution between the input and the output. Oh yeah, this is okay. Between the input and the output by marginalizing explicitly the attention variable, and that is the correct joint distribution which will compute. Now, for people who work on translation, this is clearly, they are going to clearly see one big problem with this approach, and that is that it's very expensive. When the space of y's is very large, then at this step, where for each of the input states you are creating a multinomial distribution using this softmax function over a large vocabulary, it's not going to be practical. So while this method is sounder, it's more expensive because of the large number of softmax computations you have to do at each step. So what we did was a very simple approximation which we call beam joint approximation, where instead of marginalizing over all the n possible attention variables, we will choose the b largest attention probabilities based on the probability of attention, and then just approximate this joint distribution by just summing up over the b most likely variables. Now, we could have done sampling, but then the training would become very complicated because we would have to use something like reinforcement learning, which has large variance. Other people have tried that and it does not work as well. Whereas for us, we found that with modest values of b, we are getting very good results. We also tried variational methods. They did not work. They sound good. They make for more papers, but they did not work as well as this simple idea. So so this beam joint attention, then what we would do is once you have computed the probability distribution over attention variables, you take the top k of these attention probabilities, and let's say in this example k is equal to 2, you take top 2, and over just the 2 values you create the probability distribution over the output, and then you do marginalization over a limited number of terms. So this is practical, and it's end-to-end differentiable. Sorry, it's end-to-end trainable. It's not necessarily differentiable because of the top k, but it's sort of in the same way that ReLU works, this kind of works, the top k. And it's easy and it gives us decent accuracy. So here is the performance in terms of BLUE score, which is a measure of accuracy of translation systems across 5 different tasks. We are comparing the accuracy obtained by the existing soft attention based encoder-decoder model with this beam joint model, which creates a joint distribution between the attention and the output variable, and we get a slight improvement in accuracy. This by itself may not, the accuracy improvement that we obtain by itself may not look very impressive, but recall that we have not added any extra parameters, we have not added any extra layers, we have just wired the attention differently. Just a different change, slight different change in the way in which where you marginalize the attention has caused this visible improvement in accuracy. So another task we tried on morphological inflection, there also we get an improvement in accuracy. And as I said, that we don't have to sample too many input positions. So this k denotes the number of the number of attention variables you select. And when you select just 1, then your accuracy is quite low. And but around 4, you get very close to the 6, which is what you had selected, we had selected for our experiments, the accuracy saturates. And for an easy task where we are able to actually do the exact full joint computation, we find that beam joint is very close to full joint. And this work appeared in a paper in EMNLP last year. And so now the question is, what is the, so we did a bunch of post-mortem analysis of this model to find out why is it they're just rewiring the attention slightly differently should improve accuracy. Where does it actually help? So one task where we actually have human judgment on the correct alignment between the input and the output tokens, we saw that the alignment accuracy improved from 45% to 50%. So if you think of the attention variable as alignment, then the alignment accuracy improved by using this joint attention. Another indirect evidence of improved alignment is what is called coverage. So coverage, if you look at the input side, across the different tokens that you generate in the output, there is a total amount of cumulative attention that each token in the input sees over the different output tokens. Now, if you are doing faithful translation, you don't want to ignore some words of the input. You should be attending over, if you want to not lose information from the input, you should be attending over the entire input tokens. We found that coverage, if coverage is higher, it means your attention distribution is somehow sounder, and we found that coverage increased from 73% to 83% using the transparent, the joint attention model. So after we did this joint distribution, we wondered, could we have gone a step further in treating the attention variable with more decency, like treat it as a first class citizen rather than something that you kind of marginalize away at the first possible chance. So one natural next thing you might want to do is explicitly couple the attention distribution over adjacent positions. So while generating the third word, if I looked at the 10th word in the input, then when I go to the fourth word, I should be hovering around the 10th word in the input because of the continuity of language. So there is strong coupling between attention distribution across adjacent positions. So you want to couple them better. So for that, you would want to, after you have computed the attention at each position, you want to take that attention distribution to influence the attention distribution that you compute at the next position in the output. And earlier, that coupling was done through the attention distribution you had computed without looking at YT. We proposed what we are calling posterior attention networks. So this work is going to be present in ICLR 2019, where we show that instead of propagating the attention without looking at YT, if you look at the posterior attention, which is conditioned on the output that you have seen when you go to the t+1th step, you would get much better coupling. So this is what we are calling as posterior attention. This is the attention which depends on not just the decoder state, but also on the output at the tth step. So on this posterior distribution will only be available to you when you go to the t+1th step, but then you can use that instead of this probability, which is currently what is being computed, which is the prior probability, and get better accuracy. So we show that these posterior attention networks, which is this yellow lines, bars, they provide even better accuracy than the beam joint, which is based on only using the prior attention when you couple adjacent attention distributions. And we find that with posterior attention, the alignment accuracy gives a dramatic improvement. So earlier with soft attention, which was existing in encoder-decoder model, it was 45%. With joint attention, we went to 50%. And now if we move to even posterior attention, we get a further 8% improvement in alignment accuracy. So this is one part of my talk where I established that a simple rewiring of the way in which the attention is computed and used in computing the output probability can improve accuracy, give you better alignment, is in general the right thing to be doing. Okay. So now we'll go to the next point, and this is going to touch upon the Achilles heel of the encoder-decoder model, which is the inference. Okay. So we are going to talk about, so earlier we were talking about the attention, and now we are going to talk about inference, that have we handled the inference task well. So inference depends on this beam search, which is like a top K version of the greedy algorithm for finding the sequence which has the highest probability. Is it sound? Is it the best we could do? Could we do better? Okay, so that is our focus for the next half of the talk. How does it scale across? For example, suppose I use speech, because sentences are not. That's a very good question. So actually, we have not completed that work, but one student tried to use the beam joint attention framework for speech to text synthesis task, and he reported a small improvement in accuracy, but the experiments were not systematic and exhaustive enough for us to take the work further. But this is something that I am exploring with my colleague who works in speech right now. No, this was some benchmark. I am not familiar with that. Actually, because conversational speech, your sentences are not necessarily grammatically correct. Yes. Yes. Yeah. So yeah, I'm not sure how well. I mean, that's something, that domain. I don't understand that domain very well. Yeah. So I don't know whether how well the speech how much the speech recognition systems depend on language model, and would they work well even with grammatically incorrect input? Yeah.
Two questions actually. So you mentioned something on the variational space, and can you elaborate more on that as to why that did not work?
So actually what we were trying to do is, we were trying to create a probability of attention. We were trying to train the attention. Now so we had one recognition network which would compute the attention distribution after looking at all the future Y's. Okay, and then we had a KL term which would try to match the prior attention probability AT with that, that future, that posterior attention. And maybe because of issues related to high variance, because of sampling, it just, it didn't work. We could not understand very well why it did not work, but then we were surprised that in NeurIPS 2018, there is a paper on variational attention, which is exactly the idea we were working on, and it did not work for us. But this is not the first time that a deep learning idea that I had did not work for me, but it works for others. So it's very common. But anyway, so we saw that it works for them. But we were pleased to find that the beam joint, not the beam joint, the posterior attention method that we have, which is also very simple, provides better accuracy than their method. So the posterior attention just says that we are not, of course, we will not have the advantage of posterior attention when we are predicting the Tth token, but when we condition the next attention on the previous attention, we can use posterior attention. See, this is a very subtle thing, and we were very pleased with this finding. That it's a small thing, but it has not been, no one has thought about this in the community, that you don't have to totally give up on posterior attention if your variational attention does not work.
And the second question that I had was about the analysis that you did with respect to the coverage accuracy increase. So did you observe any patterns with respect to closely related languages? Like say in Hindi and Marathi, we'd expect to have those words to be around each other. But since you were experimenting across various language groups, was there any such
Actually,
analysis?
No. See, that's where we differ. Somehow we are not really NLP researchers. I approach these problems more from a somewhat sadly neutral machine learning viewpoint. I should dig more into the NLP thing, but yeah, we don't do that enough. Yeah.
Thank you.
Yes.
Yeah, when you talk about context, it's only past or also future?
So when the input context is also future. It's bidirectional. Even in the old models and modern transformer models, they all capture bidirectional context.
Level, paragraph level.
It's sentence level.
But should it not be more paragraph level?
It should be, in fact, document level. I have seen some papers. I have not read them very deeply, but there are papers which are talking about document level context. I mean, that should help, right? Particularly when you are trying to handle like pronoun mismatches across languages. You know, the nouns which are present in the whole document might give you more clue. Yes. So, so this is. So what we observed was this, that you know, so what you see is on the y-axis, we are looking at the drop in accuracy, which is measured as blue score, when you go from doing inference using top k tokens instead of top 80 tokens. So typically, as you increase, so beam search has this parameter called beam width, which will tell you what is the number of top things that you take. And as k increases, which is the beam width increases, the sequence that you output will have higher probability, will not necessarily have a higher probability, but it almost always has high probability. So the probability of what you are predicting increases as the beam width increases. If the probability increases, you expect the accuracy to increase. Okay? Intuitively, that is what you expect, but a statistician will say, yes, you will expect the accuracy to increase only if your model is well calibrated. The y-axis had just the difference in the accuracy when you went from beam size 10 to beam size 80, and on the x-axis I had different tasks, and I was showing that the y-axis values were all negative, that even when you go from beam size 10 to beam size 80, across these 5 different translation data sets, the accuracy is dropping drastically, which is very surprising. It's like you are outputting a sequence which has, you are solving a better inference task, but your accuracy is dropping. Why should that happen? That's just symptoms of a really ill model, right? No sound statistical model should exhibit such behavior. So, so basically, you know, as I said, if your model is sound, as you increase the probability of what you are predicting, your accuracy should not drop. And that is true if your model is calibrated. So there is a notion of calibrated models, and these are models where the probability that the models attach with the prediction has a one-to-one correspondence with the probability of correctness of the prediction. So the model has been trained, say, using maximum likelihood. If you have trained a calibrated model, then the probability should kind of indicate your confidence in the prediction. So as an example of a calibrated model, if a calibrated model makes 1,000 predictions at probability 99%, then you expect roughly 990 of them to be correct. Likewise, if a model makes 100 predictions with confidence or probability 70%, then you expect to find no more than 30 mistakes in that model. So when you do beam search, you are increasing the probability of your prediction because you are solving a better inference task, and therefore the probability of correctness should increase and your blue score or accuracy should increase, but that does not happen for sequence models. And for a long time we were struggling. You know, this is something that has bothered me for almost 2 years. Then finally, on a whim, I asked a student, hey, can we at least take a look at the calibration of these existing well-trained, so-called well-trained models? There have been many publicly released pre-trained models by several researchers, say Google and Facebook and all. So what we did was, for these existing models, we measured their calibration, and to measure calibration, what you have to do is, on the x-axis you plot the confidence which the model outputs, and in the y-axis you plot the accuracy of all predictions within a particular confidence band. A calibrated model will lie totally along the diagonal, whereas an overconfident model will lie below the diagonal. So in somewhat of a natural justice, these deep learning models tend to be overconfident. Okay? So these are all, you know, they are heavily below the diagonal. which means that they output very high probability with their prediction, but their actual accuracy is lower. So now, so this is a problem of independent interest even for scalar classification, like say when you are trying to use a machine learning model to solve critical tasks, like say automatic driving or medical diagnosis, then you definitely want calibrated models. But for sequence learning, this model is important for proper functioning of the beam search inference algorithm. And when we saw that the model was not calibrated, we tried to understand why is it that the models are not calibrated. So, so the next thing that we did was try to look at the calibration of individual tokens in the output space. So here are sort of a bunch of tokens. So token 2 tokens, some random set of frequent tokens, and we measure their calibration at a token level. And we find that, of course, you will see whenever you try to take calibration plots because of small data, you will see that the plots are generally brittle. But there is one token which is like really bad. Like you look at how bad its calibration plot is. And then this token, we found out what is this. This is the end of sequence token. Now, end of sequence token, if it is poorly calibrated, it means that you cannot handle sequences of varying length very well in your model. And that explained one other thing which was ailing these encoder-decoder models is that they were favoring long predictions, short predictions. So if the end of sequence token is overconfident, then very confidently, very early on, you will predict the end of sequence token and you will terminate early. Okay. So that is one of the things which we were able to explain by looking at the calibration plots. And the second reason is again having to do with what I was talking about in the first part of my talk, which is the attention variable not being given its correct role as a first class citizen in this joint modeling of attention and output. And because of that, when you create probability of y, you do not capture the uncertainty of the attention distribution. So if you have high attention uncertainty, then your token output at that position will be even worse calibrated than when your attention uncertainty is low. Okay, that's what this thing is saying. So we used some simple techniques for correcting that calibration. So these red lines is what we obtained after our efforts at correcting the calibration, because our techniques, we did not want to retrain the models, since at that time we did not have enough resources. These are all heavy models, like this is GNMT, this is a Google model, this I'm talking about like 2016, 2017 kind of time frame. And so then we found that once we fixed the calibration, then the beam search started behaving better. And this drop in accuracy, now with the red curves, which is after the calibration, after the somewhat limited correction of the calibration, we found that the drop in accuracy, which is this weird behavior, has been captured. It has been put a bit under control, which is saying that this particular investigation, just our conjecture that miscalibration is what is causing this weird behavior of drop in accuracy with better inference was proved, okay, somewhat. And also we found that after fixing calibration, so here we did not retrain the model at all. We just took the token output probabilities which the models were giving and changed them based on certain signals. And just by fixing the calibration, we got higher accuracy. Okay. So this was about the second part. We are talking about beam search being derailed because of miscalibrated models. And last, I'm going to talk about the training objective, which is the loss function which is used for training the encoder-decoder models. So now we are going to shift focus from the inference module to this training objective. Okay. So anybody who has tried to create a scalar classification model which generalizes well will know that a very important criteria for a generalizable model is that it should introduce a margin between the correct prediction and all other wrong predictions. So margin is all important. Earlier in SVM land, people explicitly tried to add the margin, but then people understood that even when you are training a logistic regression classifier, the margin is implicit. And because these are, I told you earlier that these are like a bunch of logistic classifiers, they should have the margin. But when you use this product of multiple logistic regression classifiers to distinguish between sequences of very different lengths, then the loss function is no longer sound. It does not give the margin between a correct sequence and all other incorrect sequences, where the bunch of incorrect sequences could sometimes be much shorter than the correct sequence. So in such cases, the training objective we found was not sound. And again, this we observed when we were trying to train a model for conversation assistance. So this time I was doing, during this period, I was sort of doing my sabbatical at Google, and we had lots of data, and we had no dearth of, billions of examples, and we trained a task for conversation. And we found that the encoder-decoder model was over predicting short sequences. So this is even after we accounted for the prior distribution of short messages being more common than long in a conversation setup typically. But it was doing much worse than even the prior. So here is one plot to show that. So here on the x-axis you have sequence lengths. On the y-axis you have fraction of cases which have this sequence length. And the correct is what is there in the data. So in the blue is what the distribution of sequence lengths you see in the data. Like here it shows that 25% of the responses, 25 or more % of the responses are of length 1. You say, okay, great, good, those kind of responses, right? And the orange ones is what the encoder-decoder model predicts. And look, the most weird thing is that 26% of the responses that the encoder-decoder predicts is of 0 length. It's like you ask a question to that model, you're entering a conversation, you ask a question, how was school? And you get no response. I am very used to it, but this model does not have such a weird data set, right? So this is the situation with the bias against longer sequences. And when you go beyond length 4, then you see severe signs of underprediction of long sequences. So then we sort of thought about it, and we basically kind of did a bit of diagnosis, and we found that one big problem was the encoder-decoder model not following this basic diktat that if the loss of a model is very close to 0, then the correct y should have a margin from all from all incorrect y's, and that was not being followed. And the reasons, I mean, there are more details in this one paper which we wrote in AMNLP, but a short summary of the reason is that because of local conditioning, because when you take this probability of y and break it up into probability as a product of probability over various terms, what happens is that this is the local distribution. This causes the log probability of each correct sequence to saturate. So this log probability saturates even when the correct sequence, which might be longer, has not been separated from the incorrect ones. So we show this in diagram form. So on the x-axis, what you see is local margin. You can think of it as the training loss, okay, which is what is minimized by the encoder-decoder model. On the y-axis is what you desire, the margin. The margin, which is the log of the probability of the correct output minus the log of the probability of the predicted output. And if you have 100% accuracy, then this should be 0. There should be, they should be equal. But otherwise, when your loss is very close to 0, which is the local margin, then you expect the very few sequences to be incorrect, right? So we are talking about this in the training data itself, sorry, in the verification, I forget whether it's a training data. But the main point is that even when the loss, when the local margin is positive, which means loss is almost tending towards 0. When your local margin is 5, e to the power minus 5 is what you are thinking of as the loss. Loss is tending towards 0. Sorry, this is not loss 0. This is loss tending towards 0. And when the loss is tending towards 0, you have a huge region where the margin is negative, that the correct sequence has not been separated from the incorrect sequence. We show this over 2 data sets. And for the conversation task, we were able to propose a fix, which is to do not use local conditioning, use global conditioning. That will not work when you have to generate sequences on the fly. And this chart shows how that fix improves the model. So basically now we have shown that the loss function is also not sound, but along, a bunch of other researchers have proposed global loss functions based on reinforcement learning, like training for minimizing whole sequence blue, and those would work too, but those are very complicated to train. They no longer now have the simplicity which the encoder-decoder model enjoys during training. Okay. So now I've kind of talked about the 3 things I wanted to discuss. So what next? As I mentioned earlier, the next thing that we are excited to explore is the impact of these joint attention models on other domains like speech to text kind of domains. We had some work in ICML where we tried to propose models which can be trained for better calibration. We have not been able to apply those ideas for sequence models. We would like to do that. But in terms of more radical changes, what currently is very exciting is to abandon the full dependency of the encoder-decoder model and think about other ways in which you can capture the correlation among the output tokens. So just in the last year, there have been 3 very exciting papers, one by Google, another by, I don't remember the affiliation, some people here, and another one by Google, which proposes various ideas, one which is based on using some latent variables which you generate sequentially, but then thereafter you generate all the tokens in parallel. And then this Lee et al. Paper tries to produce the output sequence tokens iteratively. You first generate a rough sentence while generating all the tokens in your output in parallel without modeling any dependency between them. But then you refine that output. So this is now in terms of, this is the frontier of challenge for the next round of sequence to sequence learning models. And one advantage of these are called non-autoregressive models. One advantage of these models is that they do not have the latency of sequential decoding, which is actually a big problem with the current models. Particularly in applications like speech synthesis, text to speech synthesis, you don't want to generate each sort of audio frame sequentially. You would like to do it in parallel. So this is now at one problem which many people in the community are excited about. And we also have some good results in training such non-autoregressive models, not for translation yet, but for grammar error correction. And another area which I think has to happen very soon is to make these models work with humans. So I was talking with my colleague Kameshwari and Varun about correcting or editing or evaluating programs. So there you have a lot of domain expertise from programming languages. And if you see the encoder-decoder models, they're all black boxes. How do you make them interoperate with human biases like grammars? Like even for the translation, given that there are so many transfer grammars already existing, can we use them better for training more interpretable, more accurate, less brittle models using neural networks? Okay, so these are the 2 areas in which I think there is now the next frontier of improvement, from where next frontier of improvements will come for the sequence-to-sequence learning models. So with that, I will stop. Thank you.
Any more questions for Sunita?
So I'm not an ML person, so a lot of the stuff I don't have the background to comment. But this encoding, decoding, I see this in in the wireless space, because that's what my background is, and there also you have this error correction codes and those kind of a thing. Lot of, like for example, the Shannon theorem said something, and for a long time people struggled with it. And finally, some advances in the form of turbo codes and other things come. Lot of, towards the end, some of the stuff that you were telling, that you come up with some initial translation and then refine it. That's how more or less
yes.
the turbo codes work.
That's a very good
so
idea.
I'm just wondering, I see that this is turbo codes are like 1993, or even in fact, turbo codes itself, they said Gallagher had come up with it in 1960s itself.
Yes, yeah.
So what is this disjoint? It
yes.
seems like history is repeating itself in
but
terms
see, with
of...
turbo codes, turbo codes, I also teach turbo codes, because when I teach the graphical models course, I said, look, turbo codes is basically belief propagation, right? But belief propagation still has some kind of factorization, in the sense that you assume that you have a small number of parents, and therefore belief propagation works. So yeah, actually that could work. Yeah, but but it's just that for deep learning, what happens is people want to when you take the input, in turbo codes, doing the refinement steps is very efficient, because the logic is simple. Whereas when you do deep learning, from the input to output is 12 layers. And now it becomes very expensive. So you cannot do very aggressive, too many refinements. We are talking about like maybe 3-4 refinements, because you cannot go through 12 layers of logic maybe 30 times. That's one big difference. Yeah. So the dependencies are deep.
Thanks, madam. It's a wonderful presentation.
Thank you.
I was wondering, if I were to apply this to time series forecasting, multivariate time series forecasting, can I use the same architecture in toto?
That's a very good point. In fact, the encoder-decoder model is what is used for time series forecasting also. So like what people are interested in doing is not forecasting the immediate next thing, but a window of a particular horizon.
Absolutely.
So the horizon the horizon of prediction is the decoder, and the encoder is what you know in so far. So Amazon had this paper called Deep AR, which is now the de facto standard, and that is the encoder-decoder model.
Deep AR.
Deep AR.
Okay.
Yeah. So that's the encoder-decoder model. In fact, I should list that as also as an application, time series forecasting.
Okay. Thank you.
Yeah.
Okay, Saket, last question. Yeah.
Yes.
You talked about calibration, and we have faced similar issues. I work in vision, so
yes.
Any kind of deep network actually has those issues.
Yes. Yeah.
So my question is that in a way, calibration is about how we interpret probabilities and what neural networks output probabilities. So do you think making neural networks more interpretable would also sort of lead to better calibration? Are these two related?
Of course, calibration is one requirement for interpretability, but interpretability is a much broader goal, which will not just benefit from calibration, but also from several other visual and explanatory aids. Like people might, people talk about, oh, I will give witnesses with my predictions, I will give rules with my predictions. These are different other aspects of interpretability. But calibration is a prerequisite for interpretability. Yeah.
Thank you.
Okay, with that, I think we'll close the session. Let's thank Sunita once again for this wonderful talk.